Greetings, my name is John Gabriel, and this is the New Calculus channel. This presentation is a special presentation for a young friend of mine who lives in the Netherlands and wants to learn geometry, actually trigonometry, which is geometry, but a specialized field of geometry. So I'm going to, in this video, give you a brief introduction of trigonometry and how it all started. So let's begin. Now, before I continue, I have one thing to say. In order to understand trigonometry, you have to understand geometry. And in geometry, there are no axioms. You've heard the falsehood being spread for centuries now. Well, actually not that many, but for a reasonably long time, that geometry requires axioms. This is completely untrue, and in my free ebook, which you'll find at this link here, thenewcalculus.weebly.com, an introduction to the single variable new calculus, I show you how to derive every one of Euclid's 5 requirements from absolutely nothing. I don't have time to do it here because what I'm going to be doing is giving you a brief introduction, but I encourage you to go to that chapter in my book which says there are no axioms or postulates in mathematics. Okay, and the real foundations of mathematics are Greek mathematics. In other words, the elements, the works of Archimedes, and the last great publications by Apollonius. Okay. Of course, there were many other materials that were lost in the Great Fire, in the library in Alexandria, in Egypt. But in any case, that's just a little bit of background. And so we will assume now that point is a well-formed concept, which it is, contrary to a lot of the wrong textbooks, which say that it's not a well-defined concept or not defined at all, that a line is well-defined, and that a circle is well-defined, and that parallel lines and right angles are also well-defined. And of course, you'll find this all in my free book, An Introduction to the Single Variable New Calculus. So let's begin. Now, how did the ancient Greeks begin to study the problem of angles, right? I mean, so what we want to know is, how do we measure angles? So you've got all different types of angles, and I've just listed a few here. I've shown you very briefly what is a scalene, where none of the sides are equal, a right angle triangle, which has a right angle and 2 sides and a hypotenuse. You can also get an isosceles, which means 2 sides equal, and you can also have a right angle triangle, which is also an isosceles triangle. Now, the problem here is to measure these angles. I mean, how do we talk about these particular angles? Well, let's see. Now, the challenge of defining measure for these angles was solved in terms of a geometric object. Can you guess which object? Well, you could stop the video now and just think a little bit about it. Before the derivation of the number concept, whatever unit was chosen, this object had to accomplish the task of uniquely describing the measure of any angle. Okay, and this object, by the way, is actually the right angle, which is formed by perpendicular lines. Okay, now this measure was chosen by the ancient Greeks, and it came long before the systematic derivation of number and Pythagoras. Now, there have been numerous attempts by mainstream academics, especially people like Wildberger and his rational trigonometry, which is not rational and has really no improvement over the mainstream formulation, or the one that was actually handed to us by the ancient Greeks. It's tedious with no extra benefits. Moreover, it still uses those incommensurable magnitudes, which have no number to describe them. In other words, there is no such thing as an irrational number, but Wildberger uses the term irrational numbers when he says that his trigonometry doesn't have any more irrational numbers. And the first primitive angular measure was provided by the right angle, okay? And it's formed by perpendicular lines. So let's see how the Greeks solved this. Well, they begun with taking any triangle. Let's say this is the angle we want to measure, this red one, positioning the vertex at the center of a circle with one of the lines coinciding with the diameter or the radius. Okay, and a first approach could have been, well, we could measure this angle in terms of the ratio of this vertical line to this horizontal line here, which incidentally is the sine ratio. So we could say, let's start at approximately 0 and move all the way up. Start at 0. I can't really get at 0 because it's not on the grid, but you can see that every angle from this point here to this point here is unique, but as soon as you get to this stage here, then they're no longer unique. So you can only have unique descriptions for one quadrant if you use the sine ratio, okay? Now, the Greeks chose to use Radian measure, right? Let's see, what is that? So Radian measure is this. It's basically a ratio of the length of this arc on which this particular angle is subtended to the radius, okay? So it's this length divided by the radius, and that is the measure of the angle. Notice that it is dimensionless, okay? Radians do not have dimension. And how does this come about? Naturally from the constant pi. We start off with a constant pi, as you can see here, which is the circumference divided by 2 times r. And we know that the circumference is always going to be 2 pi r. So we define the measure of theta, or this angle here, as the arc length over the radius length. And it is always unique for every single angle, right? Unlike the previous little diagram that I showed you. This value here, and notice that it climbs up all the way to 2 pi, okay? All the way to 2 pi, right? So approximately pi over here, do you see that? Approximately pi if it's there, and then 2 pi once we get to this. Well, that's probably because we had 0 and the graphics is not that good, but it's 2 pi, the complete angle, all right? And so we have a very easy way to convert radians to degrees, as you see here, and degrees to radians. And I show you here both measures, the degree measure and the radian measure, okay? So the radians are here and the degrees are here. Now, once you know this, you can measure any angle in any triangle, because if you go back to this previous diagram here, you'll see that all you have to do is position the angle at the vertex, right? At the vertex, and then use the arc, this little arc, over the entire radius, all right? So that's pretty much how they came upon the idea of measuring angles. Now, the Greeks actually didn't use radians per se, but they used right angles. So, for example, this angle here would have been measured in terms of right angles. So over here, it would be approximately half a right angle, okay? 45 degrees, half a right angle, or pi over 2 radians, right? And then, of course, if it was right over there, it would be 2 right angles, or just pi, right? So now all this led to what you see often in trigonometry, and which forms a completely separate field, which are all these ratios. They're not that complicated, but you can see that all these ratios are given by the values of the lengths of these lines. And again, notice we base everything regarding trigonometry and angular measure to the circle, because without the circle we don't have a unique number for each angle, okay? And contrary to what Professor Wildberger says, his nonsense of spread and quadrants. Doesn't compare to this. It's far more complicated. It doesn't work out as beautifully as the way the ancient Greeks did it. Okay, so and this length here is the sine length, and you can see that I've color-coded them, so you can stop it now and make sure that you're seeing all the right things, and these are all correct. Now the complement, as you can see here, is simply found by using this similar triangle. So if you look at sine here will be the length of the green line to the radius, okay, to this radius here, green line to the radius. But its complement is the cosecant, which is this orange line, and I've drawn a dotted broken green line here to show you it's the same as sine, but it's this orange line over the radius, right? This orange line over the radius, and that gives you the cosecant. Similarly with the secant and the cotangent. And this is pretty much it. I will place a link to this apple so that you can download it and play with it. And then after you've understood all this, you can easily understand all the identities, the trigonometric identities, such as the sine area formula, the sine over the opposite area, the cosine rule, and many other particular formulas related to trigonometry. So, to my young friend in the Netherlands, I hope that this has been a good introduction for you, and perhaps you will now be able to study trigonometry and know exactly what is meant by all these ratios. I hope you've enjoyed this presentation. My name is John Gabriel, and this is a new calculus channel. Please become a subscriber to my BITCHUTE channel, because I will not be posting videos indefinitely to YouTube. I'll probably upload this one to YouTube as well. And I hope to be producing more videos, but it all depends on certain things like my health and where I'm going in life. So that's pretty much it for now. Till next time, goodbye.